Okay, this week we're talking about clouds, precipitation, and weather radar. So let's begin to explore and see what we can find out about these here. So how do clouds and precipitation form? We've talked about moisture in the atmosphere. We've talked about vertical motion in the atmosphere a little bit and stability. But how do clouds and precipitation actually develop out of that? Well, we know water vapor is invisible. So when you're seeing a cloud, obviously, it is not water vapor anymore at that point. It has become a liquid or ice crystals, both of which we can see. But there are sources that allow clouds to form. There needs to be what they call a cloud condensation nuclei. And you're going to really see what they are here a little bit. It talks about volcanic eruptions, sea spray, forest fires, wind, erosion of the soil. So why does that happen? Well, take a look at a raindrop versus the size of a beginning cloud droplet. A cloud droplet's over 100 times smaller than a rain droplet. So when you think about that, that means it has a very, very sharp curvature to it. And something happens with water when it has a sharp curvature. So what happens with it is when it's very curved, it allows a lot of water to evaporate a lot faster than it does over a flat surface like an ocean or a lake. So when that happens, you really need a very high relative humidity to keep it there. You actually need over 300% relative humidity, so that's not realistic in the atmosphere. So we wind up with something called condensation nuclei, which we just talked about a little bit there. Those nuclei actually create a solution within that little tiny raindrop so that that curvature effect doesn't have as much of an impact. So we wind up bringing the relative humidity down to around 100% again, where it can begin to grow with 100% relative humidity. So these little tiny nuclei, sea salt is a great example. In the Midwest, dirt blown up. All of those are ways of keeping these clouds and allowing these little nuclei to form and causing clouds in the atmosphere. So without that, there's also something that causes ice to form. Guess what? Water doesn't freeze at 0 degrees when it's a tiny little droplet. That curvature, again, continues to cause it not to freeze. So if it doesn't freeze at 0 degrees, it actually has to get down to around -10 or so. And there, when you get this dust and dirt into it again, it begins to freeze. Otherwise, you've got to go all the way down to about -32 degrees Celsius to wind up, or even lower, to wind up with everything spontaneously freezing. So you have these supercooled water droplets out there, and with that, when other water droplets actually do freeze, precipitation begins to form from this. So we're going to talk a second here about terminal velocity. Gravity pulls these rain droplets or cloud droplets down, and the air that probably caused them to form in the first place is probably rising. So unless they get big enough, they're not going to come falling down to the ground. They have to grow to a certain size to reach a point where gravity pulls it down. And there are two processes that go into effect with that. There's collision coalescence, which happens in warm clouds where temperatures are above freezing, or the Bergeron-Findeisen effect, which occurs when cloud temperatures are below freezing and you have ice in the clouds. So most times, the Bergeron-Findeisen effect in the United States is going to be the predominant effect. So most precipitation forms that way. There are times in summertime, and if you're out in the tropics, where warm clouds, temperatures above 0 degrees Celsius, you have these drops that begin to collide and coalesce together and merge and get bigger till they finally get big enough to fall all the way to the ground. And you can see an example of that here where one droplet maybe picked up a couple other ones, begins to fall a little bit, picks up a few more, and gradually it becomes a full-size rain droplet. The Bergeron fin dicing is a little different. What happens is you wind up with relative humidity over water. Saturation vapor pressure over water is actually greater than over ice. The reason for that is that water is a liquid and the molecules move a little bit quicker in it. Even though the temperature might be the same, the water has molecules that are liquid and move a little bit freer because the molecules are a little further apart. Whereas when they become ice crystals, the molecules are tightened up together so that the relative humidity required, the saturation vapor pressure required, is less over ice crystals. So what happens if the pressure is higher over water than over ice? That means the water is going to flow towards the ice crystals. The ice crystals are going to grow, and you wind up with more and more ice or snowflakes in the sky. And here you can see precipitation forming out of a cloud and falling down with virga, which is very typical. And sometimes when it's very dry in the lower levels, it's evaporating and it's actually cooling underneath that. There are different types of precipitation. We talk about rain falling. We have drizzle, which is very, very, very tiny little droplets. And here are different types of snowflakes. One of the interesting things about forecasting snowfall is determining the type of snowflake you're going to have. It can make a huge difference in the amount of snowfall at your location. For example, look at how big these dendrites are as a snowflake compared to these solid prisms at just a slightly different temperature, or these much colder ones, little platelets, columns. So if you have a half-inch of precipitation fall with dendrites, you might get 6, 7 inches of snow or 8 inches of snow. If you have it fall with these little columns, on the other hand, you may only get 3 or 4 inches of snow. So the difference, one of the questions always asked is what type of snowflakes are going to occur when you're trying to forecast how much snow is falling. And here you can see typically temperatures cool as you go up. However, if you have a warm front or a cold front coming in, the lower levels of the atmosphere might be very cold. There may be a layer above that is relatively warm, and then you go right back to cold again. It keeps getting colder. Well, when the precipitation forms in the clouds under the Bergeron fin dicing effect, it's forming as snow, and it's coming into this warmer layer. The thicker that warmer layer is, the more precipitation changes over to rain. And believe it or not, it doesn't take more than a few thousand feet to do that. So then it becomes rain again. And when it hits the ground, if it stays above freezing all the way down, it's all rain. If the lower section near the ground is below freezing, but it has stayed above for a good part of it, it's going to be freezing rain. If you have more area that's below freezing, it actually freezes the raindrops and you get ice crystals or sleet. Or if you can keep it, not melt it, and allow it to stay all snow, you wind up with snow. So one of the things meteorologists look at is just how the temperatures change in the atmosphere to see whether we're going to get all of snow or all of rain or some mixture thereof. And many times in the wintertime, different sections get different types of precip because of that. So here you can see the typical sounding of freezing rain and devastation that it causes with trees coming down and all. And you can see there was just warm section right here, probably only about 3,000 feet thick, where it's about, maybe 4 or 5 degrees above freezing. And that was enough to melt the ice of snow that was coming down. And when it did, it became back down below freezing just for a little bit right here. Everything formed again as ice, froze it on the trees, and you have freezing rain. There are great ways of looking at precipitation, and one of them is by looking at radar. Radar is just reflectivity pulses going out, and we can look at Doppler rate effect, like a train going by, and the change of what you hear, the frequency you hear as it moves by. We can translate that into a velocity. And here you just see a quick image of some tornado debris with the dual pole radar, and a weak little tornado that's right here by this town, and you can actually see a hook echo on the radar here showing it. Here's a hurricane coming in, where you can actually see the banded structure on the radar, bringing all the precipitation in and the high winds showing up here in the Doppler mode, and the different bands of precipitation, the intensity of them here. Phased array radar would be a wonderful thing to have, but we're never going to get it for many, many years because it's extremely expensive. What it is it's continuous pulses of energy going out so that it can actually see every elevation as it's going out, and you can see the whole entire cloud instantaneously. Currently, with dual pole radar, what you wind up with is an elevation change, and in about 5 minutes we can see the entire elevation of a thunderstorm. And then it goes back down and repeats the cycle. With phased array, you wouldn't have that delay. It would be instantaneous. And here you can see the rainfall estimates, or another method we get from rainfall as well. Finally, we just want to talk a little bit about clouds. There are 3 basic forms of clouds. Cirrus clouds, cirriform clouds are the wispy, very high clouds, mostly made up of ice. Stratiform clouds are layers. And yes, you can have cirrostratus clouds, so you could have a high layer of clouds. You can have altostratus clouds, which are like a mid layer. And you can have cumulus clouds too, which are bumpy. They're more impacted by the instability of the atmosphere. And here you can see the clouds coming off the Great Lakes, called cloud streets. And living in West Virginia or around the Great Lakes, anywhere, you can get these streets of clouds down. We may bring you snowfall sometimes. Another thing that happens is warm air. We just had last week a question about cold air moving across the warmer waters of Lake Superior. Well, guess what? The same thing can happen with warm air moving north across cold waters. If it does that, the cold water is going to cool the air. You wind up with fog. So with that, I just wanted to show you quickly a couple things on currently. We see here a band of clouds across the southeastern United States, stretching back into Arkansas. We also see some snow. You can actually see the snow on the ground up here to the north. And here are those cloud streaks coming right out of the Great Lakes, across them, and into parts of Michigan in this area here, and off of Lake Erie into the parts of western New York State. There's actually some fairly heavy snowfall there going on with this coming across. If you wanted to look at radar currently, this is just an image of what dual pole can do for you. It was an old picture from earlier where you have what may or may not be hail. Normally I would estimate it would be hail, but before we had dual pole, what you would see is a very bright echo in a thunderstorm. You can see almost like a hook to the shape of this thunderstorm. So you would estimate that there may be some hail in here. You're not real confident. Now with dual pole, what happens is you can see the shape of your echo. In other words, you can see the shape of the water droplet. Actually gives you a vertical and a horizontal look at that shape, because that's what dual pole does. It sends out a vertical pulse of energy and a horizontal pulse of energy. So it gives you a shape. And where the shape changes, which happens when you have ice, big ice like hail, the more the change, the more we can detect the change here and find out that in this area is the biggest hail. So right here in the northern part of this echo is where the biggest hail's falling, the little lesser hail's down this way. But by having the two combined with the reflectivity and the dual pole differential reflectivity for the change of shape of the ice crystals, we can actually detail the area, have high confidence in it, and be able to issue a warning much better. And finally, here's a radar map from the current radar, what's going on underneath the clouds that we just saw. And you can see the precipitation, just regular. Looking at high-res precipitation, the darker the greens, the heavier the precip moving east across the area. And if I wanted to, I could look at base velocity at this, and this would be the Doppler effect. And you can see here where it changes color. That's the winds coming from the southwest, moving to the northeast. As far as the radar, which is down here, goes, at that point, they appear to be one direction for the perpendicular and almost no wind velocity right along the line right here, where it's perpendicular to the radar. So these are just some of the things radar can give you. A lot of very good tools for your forecast. And now you have some idea of how precipitation forms. So hope you got something out of this, and let me know if you have any questions.